Supersonic flows don't often occur in nature. They do occur in wind tunnels like this one at MIT. We're going to look at some effects of compressibility which have to be taken into account whenever we try to produce or control a supersonic flow. The heart of the problem is the behavior of a compressible gas flowing at high speed through a converging, diverging nozzle. We'll begin with the phenomenon of choking, or sonic flow at a throat. We'll encounter shock waves and expansion waves when we come to the supersonic part of the flow. And finally, we'll look at the problem of bringing a supersonic stream efficiently to rest. Because we want to see the whole flow at one time, it's more convenient to demonstrate the same effects in this small channel. Room air at atmospheric pressure enters the channel here, flows from left to right through the channel, through this control valve, and into a vacuum pump downstream. Each column on this manometer board shows the static pressure at the corresponding point on the lower wall, the flat wall of the channel. We've arranged for the mercury level to go down when the pressure in the channel goes below atmospheric. Zero pressure is here. The first column always shows the stagnation pressure upstream, the pressure in the room. The last column always shows the downstream stagnation pressure, just ahead of the valve. At low rates of flow, the pressure is nearly symmetrical around the point of minimum area, called the throat. We can draw a continuous pressure distribution and interpret the curve qualitatively as velocity. This is because viscous forces are not important outside the boundary layers, and the fluid acceleration is determined by pressure forces alone. A falling pressure always means a rising velocity, and vice versa. The highest velocity in this flow is at the throat. If we increase this throat velocity, we come to a critical flow rate. The noise level suddenly changes, and the pressure distribution develops a corner at the throat. As we continue to open the valve, the symmetry disappears. Notice that the pressure and velocity upstream of the throat are not changing. Just downstream of the throat, the falling pressure means that the air is accelerating in the diverging part of the channel. Then the pressure rises almost discontinuously, but does not return to its original upstream value. We can see what is happening in the channel by using a Schlieren optical system to make density variations visible. The mild boiling motion is turbulence in the room outside the channel. Now, watch the throat. As the noise changes, a shock wave appears at the throat and moves into the diverging part of the channel. The position of the shock wave matches the discontinuity in pressure. Here is a close-up of the shock wave forming. The appearance of a shock wave in the channel means that the flow is locally supersonic. The difference between this symmetrical flow and this unsymmetrical one is that now the velocity is sonic at the throat. This transition to sonic flow at the throat with all of its consequences is called choking. To see why choking plays an important part in compressible channel flow, let's look at the one-dimensional momentum equation for steady flow without viscosity. Notice that changes in pressure and velocity always have opposite sign, no matter what happens to the density. We have already used this fact to interpret our manometer. Here is the same equation rewritten for the special case of reversible adiabatic flow. M is the Mach number, the ratio of the velocity of the fluid to the local speed of sound. For nearly parallel flow, we can also relate changes in density and velocity to changes in channel area by the one-dimensional continuity equation in differential form. Now let's consider flow at the throat, where the area is locally constant. We have two algebraic equations for d rho and dV. Suppose that the Mach number at the throat is not equal to 1. Then the two equations can only be satisfied if d rho and dV are 0. The velocity, density, and pressure are constant near the throat and must be going through a maximum or a minimum there. The flow has a kind of local symmetry about the throat, as in this subsonic case. Now suppose that the Mach number at the throat is equal to 1. This is the special case we have called choking. The two equations are now identical. Since both d rho and dV cannot be determined from a single equation, they need not now be 0 at the throat. The velocity, density, and pressure can increase or decrease continuously through the throat, and the flow need not be symmetrical. In particular, the highest velocity need not occur at the throat. To illustrate these ideas and test the accuracy of the one-dimensional approximation, we have computed some theoretical pressure curves for our channel. The intersection of the curves marks the conditions for which air, accelerating from rest, should reach sonic speed. Note that the decrease in sound level coincides with a change from a symmetrical flow to an unsymmetrical one, as the flow goes sonic at the throat. Downstream of the throat, we have drawn two theoretical curves. The upper branch is subsonic, with the Mach number decreasing from 1 toward 0 as the channel area increases. The flow behaves qualitatively as if the density were constant, so that continuity is satisfied to a first approximation by a balance between area and velocity. In a subsonic flow, the velocity goes down as the area goes up. Here again are the two forms of the momentum equation. In the limit of 0 Mach number, the lower equation shows that the density is literally constant. For this case, we can integrate the upper momentum equation directly. The result is the Bernoulli integral. And we can compute a theoretical pressure distribution for a given flow rate. Even when the real Mach number at the throat is as large as 1/2, as in this example, with a throat velocity of several hundred feet per second, the approximation of constant density is surprisingly good. Now let's go on to look at some properties of supersonic flow in our channel. We have roughened the flat wall of the channel with strips of plastic tape. The object of the roughness is to produce small disturbances in the flow as an aid in visualization. There is no visible effect on the flow until the shock wave appears. Then characteristic disturbances called Mach waves appear in the region between the throat and the shock wave. These Mach waves, which originate at the edges of the tape, are evidence of supersonic flow in the diverging part of the channel. So is the pressure distribution, because at first the pressure is decreasing, and hence the velocity is increasing in the diverging channel. After the shock wave, the pressure is increasing, and the velocity is decreasing in the same diverging channel, showing subsonic flow. The supersonic region ends at the shock wave. Because there is no upstream influence in a supersonic region, the Mach waves are steady. But the shock wave is not. In fact, the shock wave in this channel turns out to be not a single normal shock, but a complicated system of non-steady oblique shocks. The boundary layers are separating from the walls of the channel. This is because certain viscous effects are exaggerated when we make our channel small enough to fit into our Schlieren beam. The sound you hear is being picked up by a microphone at the channel entrance. Noise from the valve and piping can only propagate upstream to the entrance if the entire flow is subsonic. For this close-up, we have temporarily adjusted our Schlieren optical system to emphasize density gradients in the flow direction. The control valve is open just to the point of choking, and natural fluctuations in the flow do the rest. Thus, the Mach waves, the low sound level, and the pressure distribution all confirm that the lower theoretical branch downstream of the throat is supersonic, with the Mach number increasing from 1 as the channel area increases. To understand this experimental fact of acceleration in a diverging channel, we can think of the Mach number as being so large that the velocity is close to its maximum value for the energy available, and is therefore almost constant. Now, continuity is satisfied to a first approximation by a balance between area and density. The density goes down as the area goes up. The gas expands to fill the channel. For steady acceleration from subsonic to supersonic velocity, the area of our channel or of any stream tube must first decrease and then increase. There must be a throat. Since the fluid is accelerating at this throat, the Mach number there must be equal to 1, and the channel is necessarily choked. When the channel is choked and we change the downstream pressure with our control valve, we move the shock wave, but there is no other influence on the upstream flow. Because the area, pressure, velocity, and density are all fixed at the throat, so is the mass flow. We can think of a choke channel as a device for maintaining a specified mass flow from a reservoir at constant pressure and temperature. Even if we cut away the wall at some point after the throat, we don't change the mass flow in a choked channel. As long as the back pressure or chamber pressure is lower than the nozzle exit pressure, downstream conditions do not affect the flow in the closed part of the channel. When the back pressure is low, as it is here, we say that the nozzle is underexpanded. For this experiment, there is no tape on the walls. All of these waves arise from the pressure discontinuity at the corner. The Mach number is about 1.2 at the nozzle exit, and the flow is adjusting itself to low back pressure through an expansion wave. This is an ordinary air hose from a machine shop. When we look at the jet with our Schlieren optical system, we find a typical pattern of expansion and compression waves. These waves are the mechanism of adjustment to the ambient pressure. The same pattern can be seen in a rocket exhaust when the outside pressure is not equal to the exit pressure. At very high altitudes, a poor match in pressure is unavoidable, and the expansion wave at a nozzle exit may turn the flow through a spectacular angle. So far, we've been concerned with converging, diverging nozzles as a means of generating a supersonic flow. This supersonic flow may be in the test section of a wind tunnel, or it may be at the exit of a jet engine. Or the supersonic flow may be at the exit of a rocket nozzle. Sometimes we have the opposite problem of slowing down a supersonic flow. For example, we may want to bring large quantities of air almost to rest in the engine inlet passages of a supersonic air-breathing vehicle. Especially at high Mach numbers, the engine power is likely to depend strongly on the efficiency of this deceleration and compression process. Without any supervision, a supersonic flow tends to slow down abruptly through a strong shock wave with a large loss in stagnation pressure. The deceleration in a normal shock wave like this one in a large wind tunnel is thousands of millions of gravities, and the word shock is certainly appropriate. There are very large gradients of velocity and temperature inside such a shock wave, and large losses in stagnation pressure due to viscous dissipation and heat conduction. Now let's concentrate on the problem of controlling a supersonic flow, in the sense of bringing it to rest as efficiently as possible. We know that we can accelerate a supersonic stream by increasing the channel area. Conversely, we expect that we should be able to slow it down by decreasing the area. A converging channel used for this purpose is called a supersonic diffuser. We've now changed our channel geometry. First, we have a short symmetrical nozzle designed to give uniform flow at a Mach number of about 2.3 in this test section. Then we have an adjustable second throat, which can be opened or closed to vary the amount of supersonic compression. We now have two means of control over the flow in our channel: the geometry of the second throat and our original control valve. Let's begin by making the second throat smaller than the first one. As we open the valve, the channel chokes in the usual way. But at the second throat, the upstream flow is subsonic and independent of downstream conditions. All that we can do with our control valve is to move the terminal shock wave without affecting the flow upstream. Now let's make the second throat slightly larger than the first one. As the flow rate increases, the first throat chokes, and a shock wave appears in the nozzle. Then the second throat chokes, and we can no longer affect the first shock wave, only the second one. The channel is now said to be blocked, with the first shock wave trapped in the supersonic nozzle. To understand blocking, watch the shock wave moving downstream to higher Mach numbers. The dissipation in the shock wave is increasing, and the downstream stagnation pressure and density are decreasing. Let's watch that again. This time we'll keep a record of the continual decrease in pressure and also density of the subsonic flow through the second throat. Since the mass flow is fixed, because the first throat is choked, and since the area of the second throat is constant, the fact that the density is going down means that the velocity at the second throat must be going up. Finally, the second throat goes sonic, or chokes, and the channel is blocked. Now let's use our second means of control over the flow by changing the area of the second throat while the channel is blocked. Notice that the shock wave in the nozzle is moving, even though the motion of the walls is hardly visible. As long as the flow is sonic at the second throat, the density there has to change when the area does, because of the fixed mass flow. The shock wave in the nozzle therefore moves, and the correct stagnation pressure and density through the second throat are maintained. To avoid blocking our channel, we have to open the second throat a little more so that it will not choke even for the strongest possible shock wave at the test section Mach number of 2.3. The first throat has choked, but the second has not. The back pressure is still decreasing, and the shock wave is moving downstream in the channel. Suddenly, the shock wave jumps into the subsonic diffuser. We say that the channel is now started, or running, and that the original shock wave has been swallowed by the second throat. The wave pattern ahead of the second throat and the pressure distribution show that the flow is supersonic all the way from the first throat to the terminal shock wave. If we now close the control valve slowly, we drive the shock pattern upstream toward the second throat, where the Mach number is lower than the test section value because of the supersonic compression. By increasing the back pressure sufficiently, we can unstart the channel or disgorge the shock wave. And we can restart by again opening the valve. When the channel is running, we expect to be able to reduce the area of the second throat, because now there is no strong shock wave in the nozzle to degrade the stagnation pressure of the flow. But when we try this, the flow becomes blocked almost immediately. We have to reopen the second throat in order to restart the channel. In this close-up, we can see part of the reason why we cannot close the second throat to the same area as the first one. We have to allow room for these thick boundary layers, which are not carrying their share of the mass flow. As we vary the area of the second throat, notice the wave pattern changing in response to the slight motion of the walls. It's possible to calculate from the wave angle that the Mach number in the test section is about 2.1, while the lowest Mach number we can get at the second throat is about 1.4. This time, watch the manometer as the second throat is closed to block the channel. Note the similar pressure distributions at the two throats. We again open the second throat to restart, and then close this throat as far as we comfortably can without blocking. Finally, we take advantage of the supersonic compression by closing the control valve a little to move the terminal shock pattern upstream to a lower Mach number. Notice the downstream stagnation pressure increasing. Now we have reached an optimum running condition with a relatively low dissipation of energy. The advantage of using an adjustable second throat to control the airflow is that the stagnation pressure losses, and hence the power required to run the channel, can be reduced below the requirement for starting. Here we are looking down the throat, so to speak, of an engine inlet designed to operate at Mach numbers up to 3. This wind tunnel model of the same inlet duct has the top plate removed to show the means provided for varying the geometry in order to improve the pressure recovery. Since the supersonic flow is provided by the relative motion, the inlet duct corresponds to our second throat. However, the idea of a fictitious first throat is still useful for understanding the behavior of the airflow. In summary, we have seen 3 important phenomena which occur in adiabatic channel flow. Choking implies sonic flow at a throat with an upstream flow which is independent of downstream conditions. Blocking implies choking at 2 throats in succession, with the second throat area too small. Starting implies swallowing of a shock wave and is a necessary step in the achievement of supersonic compression or diffusion in channel flow of a compressible fluid.